Let's begin talking about building analog to digital converters. The simplest ADC that we can possibly build is a 1-bit ADC. We're going to use a special component here called an analog comparator. An analog comparator has two terminals, a positive terminal and a minus terminal. What we're going to do is we're going to take our analog signal that we want to convert, we're going to tie that to the positive terminal, and we're going to tie a reference voltage to our negative terminal. In this case, the reference voltage is going to be Vref divided by 2. This is simply a voltage divider here that's going to, because these two resistors are equal, it's going to take this input voltage and produce a voltage here that's going to be half that. So this reference voltage at this terminal is going to be Vref divided by 2. So what a comparator does is that its output is going to be high. That is, it's going to be whatever the power supply is, VDD, if the positive terminal voltage is greater than the minus terminal voltage. So in this case, if Vn is greater than Vref divided by 2, our output's going to be VDD, or we'll call that a digital 1, while if Vn is less than the minus terminal voltage, then the output is going to be 0, a digital 0, for the case of Vn less than Vref divided by 2. So in this case, we have a 1-bit ADC. We can tell if Vn is above Vref divided by 2 or if it's lower than Vref divided by 2. So a 1-bit ADC is not very useful. We need to be able to build an N-bit ADC. So how are we going to do it? Well, there are several different approaches. Let's talk about an approach called the Counterramp ADC. Let's say that you had a friend and you asked your friend to guess a number between 1 and 10. And your friend started saying, okay, is it 1? Is it 2? Is it 3? Is it 4? Etc. Eventually your friend would guess your number, but it may take them a while to guess your number, especially if that number happened to be 9 or 10. So it turns out that this is exactly the approach that the Counterramp ADC takes. So our Counterramp ADC is essentially going to make successive guesses at the code. It's first going to say, is it a code of 0? Is it a code of 1? Is it a code of 2? Etc. And it's going to do that by using a DAC inside of it. So it's interesting that this ADC has a DAC as part of its architecture. And what it will do is it will take its guess here, let's just say put this all zeros, output this to here, so this would be now a 0 volts, and it will see is Vn greater than this or not. If Vn is less than this voltage or equal to it, then it will say I have found the code. So in this case we have Vn is going to be, above 0. Let's say it's a code of 1001. So we'll keep outputting. So here we will keep guessing code. So here we'll do a 0001. We'll then guess a 0010 and so forth until we finally produce a voltage here on this DAC that is greater than Vn. When this VDAC here voltage is greater than Vn, we have found the code that's going to correspond to this input voltage. Now the problem with this is that it's slow. We can take multiple clocks depending upon the input voltage to actually do this conversion. If we assume that each time that we apply a new code takes 1 clock cycle, then it could actually take us 2 to the n clock cycles to do this conversion. So this particular architecture actually has a variable conversion rate. It could take only a few clocks, or it could take a lot of clocks depending upon what the input voltage is. So let's talk about successive approximation ADC. Let's assume that you hit a friend that's trying to guess a number between 1 and 10. The number they're trying to guess is actually 6, and you told your friend when they made the guess, then you would tell them whether or not their guess was high or low. So they would probably say, oh, okay, between 1 and 10, I'm going to guess halfway between that range. I'm going to guess 5. You would tell them that their guess was low. So then they would pick a number between 5 and 10, and they would probably pick, say, 7. You would then say that their guess was high, and at that point they would guess 6, and they would have zeroed in a very efficient way on the correct answer. This is exactly what a successive approximation ADC does in order to arrive at the digital code. A successive approximation ADC guesses at the code, but it does it in a more intelligent manner than what the Counterramp ADC does. It first guesses at the most significant bit by setting it to a 1. That will set the DAC voltage here to VREF divided by 2, and then it sees that the input voltage is higher or lower than that. If the VN voltage is higher than that initial guess, then it knows that the first bit is a 1. If it knows that if it finds that VN was less than VREF divided by 2, then it knows that the first bit should be a 0. At that point, it knows the value of the most significant bit, and then it moves on to guessing each of the other bits. This means that for an n-bit ADC, it takes n clock cycles to do the conversion, and it takes the same number of clock cycles regardless of the value of Vn. So let's take a look at the successive approximation example to see how this works. So we're going to use a 4-bit ADC. We're going to let our reference voltage be 4 volts. Our V input is going to be pi 3.14159, and we're going to go ahead and initialize our DAC input to all 0. So that DAC input is this input right here. So for the first clock cycle, we're going to set the most significant bit to a 1. That means that our DAC value is going to be 8. So the voltage of the DAC is going to be 8 divided by 2 to the 4th, which is going to be 8 divided by 16 times 4 volts. It's going to be 1/2 of VREF, or it's going to be 2 volts. We see that our DAC voltage is less than our input voltage, so that means that this guess of 1 was correct, so we'll leave that bit as a 1. At this point, we'll now do the next bit. So we're going to set the next bit here to a 1. That's going to make the DAC input be 12. So the DAC voltage will be 12 divided by 16 times 4 is equal to 3 volts. The DAC voltage is less than Vn, so this guess was correct as well. So we know that our first 2 bits are 1, 1. Let's move on to the next bit. So we'll set our next bit to a 1. That will give us a DAC input of 14. Our DAC voltage will be 14 divided by 16 times 4 is equal to 3.5 volts. The DAC voltage is now greater than Vn, so this guess was incorrect. We'll need to set that bit back to a 0. At this point, we're at the last bit, so we'll set our last bit equal to a 1. This is going to give us a DAC input value of 13. Our DAC voltage will be 13 divided by 16 times 4 is equal to 3.25 volts. We see that our DAC voltage is still greater than our input voltage, so this guess was wrong. So our final value, we need to reset that back to 0. So our final output code of our ADC is 1100 or 12. Let's check the result. Let's compute Vn divided by VREF times 2 to the n. That should give us what output code that we should get. So we get 3.14159 divided by 4 times 16 is 12.57. We truncate that, and we do get 12. Let's talk about one more analog to digital converter architecture called a flash ADC. Let's say that you ask your friend to guess a number between 1 and 10, and your friend is really tired of this game, and they say, you know what, I'm going to guess all the numbers at once. That way I'm bound to be right when you get this over with. And even though it's unconventional, it works. They're bound by guessing all answers simultaneously. They will hit on the right answer as fast as possible. And that is exactly what a flash ADC does. So a flash ADC generates all possible voltage bins that an input voltage could fall into, and then compares that input voltage against those various voltage bins in parallel, generating the correct result as fast as possible. So this is an example of a 2-bit flash ADC. So 2 bits means that there will be 2 squared or 4 voltage bins that our input voltage could be classified in. The first voltage bin is going to be between 0 and 1/4 VREF. The next one will be between 1/4 and 1/2 VREF. The next one will be between 1/2 and 3/4 VREF. And the last one will be between 3/4 VREF and VREF. These comparators, what they do is note that the positive terminal of each of the comparators is tied to Vn, while the minus terminal is tied to each reference voltage for that particular bin. This is going to do the comparison of Vn against all of these various reference points in parallel. Let's take a look at what the values of these comparator outputs can be as the voltage rises from 0 volts up to VREF. So initially, let's assume that our input voltage is less than 1/4 VREF, then that means that this positive terminal voltage here, which is Vn, is less than the minus terminal. So this output right here is going to be 0. Correspondingly, all these other outputs here will be 0 as well. And so the output of our three comparators will be 0, 0, 0. Now let's say that our input voltage is now between 1/4 VREF and 1/2 VREF. At that point, this positive terminal voltage of Vn is going to be greater than the minus terminal. So this output here will be a 1. This B output will still be a 0 because the minus terminal voltage will be greater than the input voltage. And finally, this guy right here, A, will also be 0. So that will correspond to this combination here. And we can see that as Vn goes into each successive bin, the next comparator turns on. Whenever Vn is somewhere between 1/2 and 3/4, we're going to have 1, 1, 0. And finally, whenever Vn is greater than 3/4 VREF, this output will be a 1, this output will be a 1, and this output will be a 1. So this table right here shows all of the possible values of these comparator outputs. This is called a thermometer code because you can see that more and more of these comparator outputs turn on as Vn rises. As a, you know, like you could think of a thermometer, as the temperature rises, more and more outputs turn to a 1. Now, this is not the final output ADC code. We need to have some combinational logic right here that's going to take these comparator outputs and produce a binary counting code. So all this is going to be combinational logic. So for an output of all zeros, we're going to want a binary code of 0, 0. For a code of 0, 0, 1, we're going to want a 2-bit code of 0, 1, and so forth. This is a very fast ADC. It's only going to be the settling time of the converter plus the combinational propagation delay of this combinational logic. Typically, we say that the clock speed of a flash ADC is going to be 1 clock cycle. However, the drawback is that it takes many, many transistors to implement a flash ADC. So this shows the architecture of a 3-bit flash ADC. Note that when going from our 2-bit flash to our 3-bit flash, that our resistors doubled while our number of comparators went from 3 comparators to 7. For an n-bit flash ADC, the number of resistors required is going to be 2 to the n, while the number of comparators required is going to be 2 to the n minus 1. The trade-off of a flash ADC is that it's the fastest possible ADC that you can build, but it's going to require lots and lots of transistors to build it. The other problem with increasing the precision, not only does the number of components roughly double, but also the fact that these comparators become more sensitive as you increase precision, and they all become more difficult to design. So let's summarize. Flash ADC offers the fastest possible conversion time, but requires the most transistors of any architecture. There are commercially available flash converters up to 12 bits, and we say the conversion is done in 1 clock cycle for a flash ADC. A successive approximation ADC, on the other hand, has a good trade-off between its performance versus the number of transistors it takes to implement. It takes 1 clock cycle per bit, which is better when compared against a Counterramp ADC, which could take up to 2 to the n clock cycles for a conversion. And it only uses 1 comparator, which is good when compared against a flash ADC, which requires 2 to the n minus 1 comparators. It turns out that most microcontrollers that have ADCs on chip use a successive approximation ADC because of the good trade-off between performance and the amount of transistors that it takes to implement it. There are commercially available high-precision ADC, successive approximation ADCs, that offer 16-bit conversion. So how do you build a DAC? The most common architecture is a very efficient architecture that is called an R2R ladder DAC. It consists of 2 components. The first component is a resistor ladder. This resistor ladder has 2 values of resistances, R and 2R, and it has switches that connects points in this resistance ladder either to ground or to VREF. This particular diagram here shows a 4-bit DAC. These switches here will correspond to a 4-bit code that is going to be equal to the binary weighted DAC value that we wish to provide a voltage for. When we connect a particular switch to VREF, that's going to have a value of 1. If we connect a particular switch to ground, that bit will have a value of 0. So once we arrange the switches for the binary code that we want for our DAC code, we'll get a voltage out here that's proportional to that binary weighted code, and then all we need to do is we need to provide a driving current for this output. We'll do that via an op-amp that is connected in what's called a voltage follower configuration, and all this does is it replicates this voltage on its output and provides current drive for whatever load is attached to the output of the DAC. While the key timing parameter for an ADC is conversion time, the key timing parameter for a DAC is settling time, and that's the amount of time it takes to produce a stable output voltage once the input code is changed. It turns out that for commercial DACs you can buy either voltage or current DACs. A current DAC means the output, it produces a output current instead of an output voltage. We're going to use a voltage DAC, and the one that we're going to use is going to be an 8-bit voltage DAC that has a SPI interface from Maxim Semiconductor. So let's talk about the analog to digital converter that's available in some PIC24s. It's a successive approximation architecture. For the PIC24H, it can be configured as either 10-bit or 12-bit resolution. The reference voltage can either be VDD or a separate voltage that you supply. It can sample multiple inputs. That means it has more than one input channel. For a clock source, you have two choices. It can either be a divided system clock frequency, or it can be an internally generated clock. If you use a divided system clock frequency, you must make certain that the ADC clock period is not less than 76 nanoseconds for 10-bit mode and not less than 118 nanoseconds for 12-bit mode. It turns out that the internally generated clock has a period of about 250 nanoseconds, so we will use this clock in our experiments because it's guaranteed to work with either 10-bit or 12-bit mode regardless of the system clock frequency. The PIC24 ADC is a very complicated device, and we're only use it in a very simple mode in our examples. Any pin that is marked as an ANX input, so AN1, AN2, so forth, can be used as an input to the ADC, and that means that we can sample the voltage on this pin and convert it to a digital value. This diagram here shows a model of the electronics that are on an analog input pin. When we were talking about a successive approximation ADC, we said that the conversion time is equal to 1 clock per bit. However, that's not exactly true. There is actually another component to the conversion time that is called sampling time, and the total conversion time will be the sampling time plus 1 clock cycle per bit. So what is sampling time? If we look at this model of this electronics, we notice that there's a switch here and there's a capacitor here. To make a conversion, we will first close this switch and transfer our input voltage to this capacitor. We'll charge up this capacitor until this capacitor voltage here becomes equal to the input voltage. This capacitor is called the holding capacitor. The time it takes to charge up this capacitor is called the sampling time. Once we have made this holding capacitance voltage equal to the input voltage, we will then open this switch and convert this voltage. We want this voltage to remain steady during the conversion, which is why we're going to open this switch, because this voltage out here can be changing and we want this to be a stable voltage. This process of closing the switch, charging up this holding capacitor, and then opening the switch is called a sample and hold operation. In our code examples, what we're going to do is we're going to use 31 clocks to sample this input voltage to charge up this holding capacitance. That's the maximum allowable. And then we're going to use 12 clocks to do the conversion, assuming a 1 clock per bit, assuming a 12-bit conversion. On the PIC24, there's also 2 extra overhead clocks that are required. So a total conversion for a 12-bit conversion will take 45 clocks. 31 to sample the input voltage, 12 bits to actually do the conversion, 1 clock per bit, and then 2 clocks of overhead. The internal clock has a 250 nanosecond period, so a total conversion will take 250 times 45 clocks, 250 nanoseconds times 45 clocks, which is going to be equal to approximately 11.25 microseconds. We'll wrap up this lecture by discussing voltage references. The stability and accuracy of voltage reference is critical for high precision conversions. In our lab experiments, we're going to use VDD as our voltage reference simply for convenience, but we will be throwing away at least 2 bits of precision due to VDD fluctuations. There are many different commercial voltage references you can buy in many different voltages. Here are just some typical examples. It turns out that our PIC24H device can only use a voltage reference of either 3 volts or 3.3 volts. Besides accuracy, the other key parameter for a voltage reference is stability over temperature operating range. You need this to be less than 1/2 of a least significant bit value if you want your least significant bit to mean something.